the projector's not working, so I'll record the audio. Hopefully at some point it'll come back on, but for now we're gonna do old school. Okay, so maybe we can look at homework later, towards the end of class or something. So this is 8.4, example 4. We've got a definite integral. And for these, what I would recommend is just to find the antiderivative first, using trig substitution. Substitute back in for x, and then plug the bounds in. So antiderivative. Substitute back in for x. Then evaluate the bounds. No, this is from our notes. The board's not cooperating. All right then. So what is this? What Pythagorean identity does this look like? Yeah, because we have tangent squared plus 1 is secant squared. So we're going to factor out the 16 from the denominator. It's going to be 1/4 out of the root of the denominator, rather. 1/4 square root of the quantity x over 4 squared plus 1. Right, yeah, and then our substitution, let x over 4 equal to tangent of theta. Yeah. Oh, okay, sure. Should have brought my sunglasses. Sorry. That's all right. So bright. Okay, so then we've got to figure out dx. So what is dx here? Yeah, 4 secant squared theta d theta. So I'm just gonna fill this in here. We got tangent theta, or dx, 4 secant squared theta, d theta.
Why 4 of them?
Because that was what dx was. Because we have, another way to look at this is that x is equal to 4 tangent theta,
Okay.
and then we take the derivative to get to here.
Okay.
So we're just going to compute this first and worry about the bounds later. All right, so let's see what we end up with here. 1/4 is the integral. We have 4 secant squared theta on top. And then we have the square root of secant squared. Bottom. Is everybody okay with that? Yeah, well, we cancel the constant, we'll simplify the root, simplify the integrand.
So that just become secant theta?
Yeah. So I would just recommend doing these things one step at a time, because sometimes these constants are easy to put in the wrong place or forget, or whatever, missing a sign, whatever the case may be. So we've got secant squared over the square root of secant squared. Which just gives us the antiderivative of secant. And do we know the antiderivative of secant? Part of it's right. ln so you might have to look back earlier in 8.3.
Tangent?
Nope. Nope.
We just got through this.
No, because secant is.
Secant theta plus
One over cosine.
Secant
No, secant
theta
one cosine secant. Oh, secant.
plus tangent. And we won't worry about the constant because it is a definite integral. So like I said, you got to know those ones from 8.3.
Yes.
Okay, and then we need to resubstitute now. We found the antiderivative, resubstitute for theta. So we got to determine secant theta and tangent theta. We know tangent theta already. We have tangent of theta was x over 4, which makes the hypotenuse square root of x squared plus 16. Okay, so that triangle allows us to get secant theta in terms of x, and we already know tangent theta in terms of x. So that's ln absolute value. Secant theta would give us what? Plus tangent theta was x over 4. Questions on that? Yeah.
You just explained again real quick how you got that secant in terms of the triangle, the x squared.
Yeah.
Seems
So we based it off of our substitution. The fact that tangent theta was x over 4 gave us the opposite and adjacent side. Pythagorean theorem to find the hypotenuse. And so the secant of that was the hypotenuse over the adjacent. Any other questions? So for all intents and purposes, this is our antiderivative. We can simplify it a little bit, keeping in mind our bounds here are from 0 to 1. And what we can do here with our expression, we have the natural log absolute value of this plus x all over 4. So let's write it like this: absolute value of 1/4 times all of this. Now, I mean, this step isn't necessary, but it can simplify things, especially when you're plugging bounds in. So if you can remember the property that says if you take the log of a product, what does that turn into?
addition of 1 plus log.
Yeah. Addition of the factors log of m plus the log of m. So we can do that here. ln 1/4 plus ln absolute value square root x squared plus 16 plus x. Well, it's, yeah, 1/4. It's 1/4. So, but the idea in doing this is, again, this is our antiderivative. We're then gonna you look at the definite integral. This ln of 1/4 now is just another constant. And if you remember just the nature of the way the fundamental theorem of calculus is set up, it doesn't matter what constants you have in there. When you look at a definite integral, those constants always subtract each other out.
How do you explain how you have more than 1/4?
Here,
Yeah.
it's just from this property of logarithms.
And that property of logs is when m is a constant and n is some variable, or can they both be variables?
Yeah, it doesn't stay, right? It's just m and n, whatever they are. One thing times another thing, we can break it up like that. So, you know, the natural log of x times y is the natural log of x plus the natural log of y. Remember, the analog to logarithms are, I guess they're not analogs, but the way we think about logarithms are, they are exponents. So when we multiply exponents, right, with similar bases, we multiply those two things, we add their exponents, right? So this law is comparable to saying x to the second times x cubed, or x to the m times x to the n equals x to the m plus n. So we have this product that turns into this sum. Since that's a constant, you know, that's absorbed in with our other constant of integration over here, right? We had some constant of integration here. And this constant, now with ln of 1/4 as another constant, they get absorbed into the same constant, right? Because this thing and this thing just make another constant. So when we look at the definite integral, really we just need to pay attention to this part right here, the ln of the absolute value of that. Fingers crossed. Do y'all have any questions on that? It's fine. If this seems weird, that's okay. This is the antiderivative. Just plug in 0 and 1 into this if you want. I mean, this is not a necessary step. We're just making things a little bit easier on ourselves. Yeah. So when we need these here, if it's just the antiderivative, but we're looking at the definite integral, so those constants will go away.
Projector's working.
Oh, hey, cool. All right, let me kind of get caught up here. Turn these off now. Does it look fuzzy? Or is that okay?
Always look fuzzy.
Okay.
Can we dust that little screen?
It's actually on the inside.
Oh, good.
Yeah. Last semester, it was the one they put up had a giant scratch on it, so there was this like black shadow on the board the whole time. It's awesome. Now just get us caught up for those that aren't here. I'll reference this next. that this is fine. If you want to plug in the bounds now from 0 to 1, that'll get us there. Simplify this a little bit. We've got the natural log absolute value of 1/4 times all of this stuff. I don't think this is, like I said, an absolutely necessary step to do. So then, for the definite integral, we can just use ln absolute value of this thing plus x. Can we get rid of the absolute value?
Yes.
How come?
Our bounds are
Since x is in the interval from 0 to 1, according to our bounds, the square root of x squared plus 16 is a quantity that's always positive, plus 0 or some number that's always positive. We don't need the absolute value bar or whatever. So let's rewrite this. The integral from 0 to 1 dx over the square root of x squared plus 16 is the natural log of the square root of x squared plus 16 plus x evaluated from 0 to 1.
Oh, that constant is what?
Yeah, right. You can keep it in there, but they'll just subtract out. Yeah.
Will you ever mark this down if we leave the absolute value sign? Because a lot of the times, like, I make mistakes and I think I don't need it, and I take it out, and then
Yeah.
I start needing it.
Yeah, when in doubt, just leave it.
Okay.
Yeah, if you need it and you take it away, I would probably count off a point or something. So yeah, when in doubt, just leave it. It's fine. Okay, so we got ln of evaluated at 1, ln of 17 plus 1, minus evaluated at 0, ln of 4. That's our exact answer. Properties of logarithms, again, we could rewrite this. Yeah, right.
We have to add back ln 1/4.
No, that was a constant that got absorbed with the other constant.
I see. Okay.
So it's in there. See, it's ln 1/4 is in here, minus ln of 1/4 in here. So they're adding up to 0. Or we could write this as a single logarithm. It's the natural log of root 17 plus 1 over 4. Either way, that's how we would deal with those. Otherwise, you then have to turn in your limits of x from 0 to 1. You have to use your relationship x is 4 tangent of theta, or x over 4 is tangent of theta. So when x is 0, what theta values does tangent equal to 0, right? You have to solve those trig equations to convert your bounds. So in this instance, it is, I think, easier in most cases to turn back everything back into x before you evaluate. Do you have any questions on that example? Let's just mention what happens here. I'll write down the answer. We've got to pick up the pace. So factor out like we have been doing. The 81 gets factored out. Square root of 81 comes out as 1/9. So this is dx over the square root x over 9 quantity squared minus 1. And then so what would our substitution for this one be? So it's secant. Well, if you have cosine squared minus 1, is that sine squared? No, because sine squared plus cosine squared is 1. So it's 1 minus cosine squared would give you sine squared. Here it would be like saying cosine squared minus 1 is sine. You wouldn't want to make that substitution because it's not true. The substitution we make is secant, because secant squared minus 1 is tangent squared.
That equals x equals 9 secant.
Yeah, right. That's where you would start off if you're from your textbook. Your textbook would say that your substitution is x equals 9 secant theta. Oops. 9, whatever. Okay. Also, be aware that, especially with secant, when we make this substitution, like I said, the ones that are given to us will have like this x is larger than 9. We want x to be larger than 9 because secant is not defined for values of 1, right? So if x is larger than 9, it's like 10/9. So we're getting well-defined values for secant. The long and short of that means for us, when we take the square root of this right here, we don't have to worry about the absolute value of tangent. Okay, so that's our substitution. We'll look at another example with a secant, I think, the secant substitution, but this is what you should get, setting that up, and the final result is ln absolute value of x over 9 plus the square root of x squared minus 81 all over 9. And then we have plus our constant. And the same trick we applied to the last example, we could apply here. That 1/9 is like playing the role of that 1/4. So, or we could say that it's the ln absolute value of x plus the square root of x squared minus 81. We'll call that constant 1. Constant 2 is then constant 1, C1, and the natural log of 1/9 put together.
What's our next test?
Yeah,
I think.
March 12th. Yeah, we have 2 more sections in Chapter 8 and 2 short sections in Chapter 9. All right, so I'm happy to look over that if you need to. So if you try that and you can't figure it out, look at it.
Just that question.
Sure.
The sections for 9 aren't up yet on Teachability, right?
Yeah, so I've got to make, something went crazy with those. I've got to redo them this weekend.
Oh.
I'll print those all out for you, because, I'll have them, I might have them available Sunday or Monday, but since they're not already up, I will print out chapter 9.1 and 9.3 for everyone and bring those to class on Tuesday. All right. Similar kind of example here. Let's see how this one turns out. Usually when you see the difference of squares or the sum of squares under a radical, those are perfect choices for a trig substitution. However, we did have one example where it was, I think, 81x squared plus 1 to the second power. So, things like that are also candidates as well. Factor out the 81 from the root. I have y over 9 quantity squared minus 1 all over y dy. Similar structure under the radical as we had in that last example, right? We've got a square minus 1. Our substitution x over 9 is the secant of theta. Dx is 9 secant tangent.
dy.
Oh, yeah. Thank you. Yeah, y over 9, sorry. All right, is that sufficient for our substitution? Okay, so this turns into, what do we get? We have 9 times the integral of what?
Shouldn't we figure out what y equals multiplied by 9?
Yeah, we're going to account for the thing under the radical, but we also have this y hanging out. So what is y? 9 secant of theta. So that's secant squared theta minus 1. Y, just y itself, is 9 secant theta, and dy, another 9 secant theta tangent theta. So this 9 and this 9 are gone. We've got this secant and this secant gone. So what did we end up with?
9
Yeah, 9 times tangent theta for the root times this tangent theta. This one here is tangent as well. This is tangent. Everybody okay with that? Okay, then how do we integrate tangent squared?
Could you just change it? Because I did it.
Which one?
Secant squared theta.
Yeah. So to integrate tangent squared, we're going to rewrite tangent squared as secant squared minus 1. Because I know the antiderivative of secant squared and the antiderivative of 1. So that's 9 times antiderivative there, tangent theta minus theta. And then we'll have this constant here. Yeah, they'll combine to another constant. Converting back, we have x over, was it x over 9? Is our substitution. Was secant.
Y over 9.
Yeah, y over 9. Not bad. Y over 9, secant theta. So the opposite side, square root of y squared minus 81. So we have 9 tangent theta. I'll just write this right. 9 tangent theta square root of y squared minus 81 all over 9. Minus theta, which is the inverse secant of y over 9. And then we have this constant. All of that now gets multiplied by 9. Anyone have any questions? I hope at this point, I hope you've had a chance to do a couple of these from the homework, or at least look over the notes, because it's a lot of content really quickly. You feel all right with that? Yeah? No? Maybe? Don't care? Impartial?
Memorizing
Apathetic?
identities is starting to seem like a good idea.
Yeah, for sure. Yeah, I mean, and I guess depending on what textbook you use for Calc 1, it doesn't seem like any Calc 1 courses that I've looked at or textbooks that I've looked at, they're never really that heavy on trig. And then all of a sudden you get to Calc 2, stuff like this, right? And it's I don't know. It seems kind of odd. Sometimes we need to remember the technique of completing the square for something like this. Something like this also, maybe not this one precisely, but things like this. Will become easier, I guess. That's relative. In the next section. So what we need
The
to
next section is horrifying.
no, the next section is really a technique that you would see in algebra, a college algebra class. It's probably just not a technique that you spend any time doing in algebra class, unfortunately. The textbook does mention the process, and we'll look at it, but you know the process in A5, any algebra textbook you open will have that process. For now, we've got to complete the square on x squared plus 2x plus 37. So when we complete the square on that, what do we get? You remember we take half of this number, square it, add that in, subtract that in. Okay. So we take half of 2, which is 1, square that, which is 1. So we add 1 there, we subtract 1 here. This is a perfect square. X plus 1, quantity squared. Plus 36. look that much better. But we've seen a couple of examples like this, though. What would our next step be to finish that?
X plus
Okay, well, we could. I mean, we could say that this is tangent, the tangent squared plus 36, though, not secant squared, right? Tangent squared plus 1 would be.
There's almost an x plus 1 on the top.
Yeah, there's almost the derivative up top, right? 2x plus 2. I guess there's a couple of ways to look at this. The way we chose to look at it in our notes, a couple of examples. We said let u equal to x plus 1. So we ended up with the integral of u squared plus 36 on the bottom. Du is dx. And so what is 2x plus 1 in terms of u? 2u minus, yeah, 2u minus 1. Because our substitution says that x is really u minus 1. So 2x is 2u minus 2. So 2x plus 1 is 2u minus 1. So that's 2u minus 1. And why is that a little bit more helpful than what we had? What do we do from there?
we break up the integral, and you have a tangent substitution below.
Yeah, right. So we split that up. We split this up as 2u over u squared plus 36 minus the integral of 1 over u squared plus 36. So as mentioned, this is the left integral, inverse tangent. What about the first antiderivative?
You would want to do a second u substitution.
Yeah, so we would need a second substitution here, or we notice that the derivative of the bottom is the top, right? So that's already in logarithmic form. But if you don't notice that, logarithmic form is just a shortcut process for another substitution, really. So this is already in log form. Yeah. Quantity that's always positive. Minus, what is this second integral? You could use a trig substitution, yeah. Factor out the 36. But even easier than that, it's our tangent, right? 1 over u squared plus a squared. So we have 1 over a, inverse tangent of u over a, where a is 6. So yeah, another substitution for this one and a trig substitution for that one would also work. And then we'll resubstitute. That's, what was that? X plus 1 squared plus 36 minus 1/6 inverse tangent of x plus 1 over 6. Let's see. the
Okay.
functions, and its derivative on top.
Okay.
Because in those situations, it's always going to be u equals the bottom, and then you end up with like 1 over u. Integrating 1 over u gives you the natural log. Any other questions?
Why did you get rid of that absolute value?
The u squared plus 36 is always positive, or you can say x plus 1 squared plus 36. It's always positive. So try to look at this in a different way. Someone mentioned, didn't you mention that this was almost the derivative of the top? So the derivative here on the bottom is 2 times x plus 1 to the first times 1 plus 0, right? So that's the derivative of the top, is 2x plus 2, right? So we don't have a 2x plus 2 up there. But what if we did something like this, where we said, I want this to be a 2x plus 2, so I'm going to add 1 into the integrand, and then what would I do?
Subtract 1 somewhere else.
Subtract 1 somewhere else. So what is all of this right here? All of this turns into the antiderivative when we take it as what? It's in log form, isn't it? Yeah, and then this, well, that's inverse tangent, right? Because here's your argument, here's a squared. There's your x squared, there's your a squared in that formula. Remember this x, it does get affected depending on what it is, but here with this linear, if we looked at the derivative of the inside, which is x plus 1, the derivative of that is already 1. So we don't have to worry about dividing through by anything additional, right? So like if it's the derivative of, or the derivative of sine is cosine, the antiderivative of cosine, right? We don't have to worry about that 1 over a being a part of that, because the inside function's derivative is 1. It's the same thing here with this. If we think about 1 over this quantity squared, where this, whatever this quantity is, if the derivative of that is equal to 1, then we can just call that thing, it's the same thing as this x, when we write 1 over a inverse tangent of x over a, right? So this is minus from the minus 1, and this is 1 over x squared plus a squared. So that's 1 over a inverse tangent of the argument whose derivative is 1 over a. So that's the same answer that we got in the original.
That was
Any questions on that? So it's nice to have multiple ways to do things, because just because I'm doing something one way doesn't mean there's not another way to do it. And if you can remember these techniques, then you have more tools to fall back on in case they're extra fail-safes, really. Sometimes, as we've seen though, there's really only one way to approach the problem, which that kind of stinks when that happens, but okay. All right, I think that was our last example now. questions before we move on?
Or recommended what you have to do. Splitting off the secant x tan x, or am I splitting off the this?
Right.
I don't know, let's try the long way first.
Let's pick a way and do it.
So you're busy with hair, I can distribute.
So this handout is the procedure, well, part of the procedure. Specifically what we're focusing on is how to break these things down. So this handout, thank you, is showing us, depending on what kind of factors you have in the denominator, that's how we're going to break those down. I forgot to put that in your actual notes. So maybe you need to reference that. That way you have it. Okay, and then this section we're looking at partial fraction decomposition, and the idea of partial fraction decomposition is, for example, we've got a rational function here, 3x over x squared plus 2x minus 8. The process of partial fractions allows us to break this up into fractions. And in thinking about what we're doing, there's something like 3x over x squared plus 2x minus 8 would be harder to integrate. However, if we break it up according to partial fractions, then we have something that's easy to integrate. So what would be the antiderivative then of this right here?
Rewrite those x minus 2 to the negative 1, and then x plus 4 to the negative, plus x plus 4 to the negative.
Yeah, and then
Log is 2. Yes.
so yeah.
The two.
Huh? Oh yeah. Sneaky.
We were on that. Good job, guys.
Yeah, 2. So that's the idea of breaking these down into partial fractions. We don't have to, we don't have to trig substitute. We don't have to do other techniques. Just keep in mind when we have something like this first example, 4x squared plus x minus 5 over x squared, we can rewrite everything over x squared. So we can simplify this before we take the antiderivative. So this would be something here that we could, the remaining terms, we could use the power rule on those. Whereas something like 2x minus 1 over x squared minus 5x plus 6, we have to think about this, or we're going to think about this as 2x minus 1, or x minus 3, and x minus 2. We're going to start looking at, does the denominator factor? If it does, how does it factor? Depending on how the denominator factors, if you look at that handout, will determine how we break, or how we start to set up and find the partial fraction decomposition. Okay, and we'll look at that in a moment, but the idea here is you've got two linear factors that aren't repeated. So that first one where it says the partial fractions with simple linear factors, we would end up breaking this integrand down according to that formula, where it says P of x over Q of x. I think I put that in here. I did not. So it all depends on how your, I guess your polynomial in the denominator is factored, and that determines what direction we start to head in. Before partial fractions, though, you've got to make sure that it's in lowest terms, which means that the degree of the numerator is less than the degree of the denominator. I guess And what we're talking about especially with partial fraction decomposition, is rational functions, a polynomial over a polynomial. So if that's not the case, as we've seen in many examples, then we have to use long division. Sometimes a problem involves first doing long division, and then the remainder over the divisor part, we have to use partial fractions on that to keep breaking that down. Okay, so the three that you have on the handout are simple linear, repeated linear, and simple irreducible quadratic factors.
We also have
You have what? Yeah. So I didn't put that on the handout, but I do have that repeated irreducible quadratics mentioned. We'll mention that, but we don't see any of those. So like examples of simple linear factors would be like x, because when we see x as a factor, it's x minus 0 is a simple linear factor, x minus 1, x plus 4, etc. 2x, we can put some more in here. 5x plus 4, whatever. Repeated linear factors would be things like x minus 1 squared, x plus 4 cubed, so forth. 5x plus 4 to the 7th. Simple irreducible quadratic. So you have quadratic factors, and specifically those quadratics are irreducible.
some of that being squared.
Is what? Sorry.
Being squared.
Well, that kind of depends on the problem, like what's going on in the integrand. But as far as just a simple irreducible quadratic factor goes, how do we know that a quadratic? How do we know a quadratic is irreducible? Like if I have x squared plus 4x plus 4, sometimes by inspection we can say, well, that factor is like this, right? X squared plus 4x plus 4 is really just x plus 2 squared. So that would be repeated simple linear. That's not an irreducible quadratic. How do you know if you have an irreducible quadratic? Sometimes most of them you can look at and determine that it doesn't factor in the sense that it does not have, like, how should we say, the irreducible quadratics do not have real zeros. They have imaginary zeros. If you're ever in doubt, then irreducible quadratics, just check the b squared minus 4ac part. The b squared minus 4ac of a quadratic was the discriminant and that told us the number and types of solutions. If the discriminant is negative, remember that thing right there is under the radical in the quadratic formula. So if that thing's negative, you have imaginary solutions. Examples: x squared plus x plus 1, x squared plus 1, x squared plus 9, so forth. Those are irreducible quadratics. So you see from your handout, if you've got an irreducible quadratic factor like x squared plus x plus 1, the way we decompose that, or start to the process anyways, is we just write capital AX plus B over the quadratic. And then the process is we always equate what you have on this handout, where you have the A's over the factors. You always equate those things back to the original function, because you've got to solve for all of those A's. You got to solve for that A1, that A2, AN. In this situation here, the AX plus B, we have to solve for that. And then repeated irreducible quadratics. We have x squared plus x plus 1 repeated. So like that to the third power. X squared plus 1 squared, so forth. We don't really encounter those, however. So if I look through here. So if you want to make a note on the handout, under your procedures, we have simple linear factors. We'll just look at an example of one of each just to see how that works. So, for example, if we had 2x over, let's say it's 2x plus 3 over the factors x minus 1 times x plus 2. So that's like what we just wrote down, that's like your P of what they're calling P of x over Q of x. For us, that would appear in an integrand, and then we'd have to take the denominator and factor it and say, oh, it's too simple linear. So off to the side, we would write this, and then we would say that's equal to A over x minus 1 plus B over x plus 2.
A would be 2x and B would be 3, right?
Kind of, yeah, but not really, because we've got to now take this equation and solve for A and B to figure out how that rational function decomposes into those two fractions. So they say A1, A2, A3. We could use A, B, C all the way to Z. If we needed more, we could say A, AA, B, B, C, whatever. Doesn't really matter what we call these constants. But the idea is that now once we've set that up according to the denominator, now we have to solve for A and B. So what you end up with is you end up with a system of equations that you have to solve usually to determine what A, B, C, D, E, F, G are, depending on how many constants you have. For the repeated simple linear, that would be something like if we had like x plus 4 over x, well, let's do one of these, over x minus 3 cubed, let's say. So notice in that procedure it says it's a1 over x minus r. Then it's another constant over x minus r squared. Then it's another constant over x minus r cubed. So it's all the way up to m, which would be the power that we had expressed in our integrand. So this thing needs to be written as many times as it appears with increasing powers. This. And then we'll have our constants over that. So a over x minus 3 plus b over x minus 3 squared plus c over x minus 3 cubed. And then the situation here is now solve for a, b, and c. Irreducible quadratics. So if we had, I don't know, 5x plus 2 over x squared plus x plus 1. Then we would equate that to ax plus b over the irreducible quadratic. They'd probably be a little bit different because here it's easy to solve for a and b. But that's the idea of what your handout's saying. The repeated irreducible quadratics would follow the same pattern, but we would have, you know, like if we had x squared plus x plus 1 to the third, then we would break that up as the irreducible quadratic over ax plus b plus the irreducible quadratic to the next power over cx plus d plus irreducible quadratic to its final power over ex plus f. Then we would have to solve for a, b, c, d, e, and f.
Hooray.
Yeah, but we don't see the repeated irreducible quadratics. Do y'all have any questions so far?
How do you determine which one to use?
Depends on the integrand and how the denominator factors. Okay, so we'll take a break, but so for example, when we have to integrate something like this, we say, well, I'm integrating a rational function, maybe partial fractions is a good choice. So I would ask myself, does the denominator factor? Can I factor the denominator? Yeah. Whoa. So how would the denominator factor then?
X minus 5 and x plus 1.
Okay. So then from that, I'm going to use my, I'm going to take my 3x plus 5 over x minus 5 x times x plus 1. And it's this case right here. I'm going to equate my integrands to a over the first factor plus b over the next factor and solve for a and b. Okay, so before we do that, let's take a break though. Okay, so we break this down, we factor the denominator. Based on how that factors, then we're able to choose one of the three scenarios. That's simple linear factors. 3x plus 5, x minus 5. So then, kind of like it's side work, we're going to say that 3x plus 5 over x minus 5 times x plus 1 is equal to a over x minus 5 plus b over x plus 1. And we're going to solve for a and b.
So A and B wouldn't be 3x and 5?
No. No. A and B are actually going to be numbers. So that when we do add the A plus the B part, we do get 3x plus 5. When we multiply them too, because this over here, the denominators are multiplied. Here, they're added, right? So we got to think if we were going to add A over x minus 5 plus B over x plus 1, we have to multiply the first one by x plus 1 over x plus 1, and the second one by x minus 5 over x minus 5 before we added those together, right? So it's the reverse process of that. We've got an equation involving fractions. So we'll go through this like step by step, and I'll mention 2 ways to solve these. One way doesn't always work, so we want to mention that. But we're multiplying this equation through by x minus 5 times x plus 1 so that we can get rid of the fractions. So we have 3x plus 5 equals to what? Yeah. A times x plus 1 plus b times x minus 5. It's just a cross multiply situation on the right to get rid of those fractions. But really what we're doing is multiplying through by the denominator x minus 5 times x plus 1. Everybody okay with that? So then we've got, okay, here we go. One way to do this, the most generic way to do this, we'll call it the hard way. And just hard is a relative term. So some, I've seen some of these, not in our homework or anything, but some of these you do have to, the system is so large that you do have to use matrix to solve the system. So anyways, what we need to do is we need to equate the coefficients to figure out what a and b are. So we have 3x plus 5 equals to ax plus a plus bx minus 5. Yeah, 5b. Yeah. And then so we've got to look at, over here we had 3x. So we have to equate that with the terms that have x's in them on the right hand side, with the ax and the bx. So we get, we'll call this equation 1. We have 3x equals to ax plus bx.
It started over there.
Yeah, it started over there.
You guys need these?
No.
And then we equate the constants. We've got 5. Constant over here is a, and we've got a minus 5b. So equation 2 says that 5 is equal to a minus 5b. Yeah, there's multiple ways to solve systems. But before we do that, notice 3x is ax plus bx. The x is really redundant at this point, right? So we know that whatever x is, it's here and here. If we factored the x out and divided through, we would have 3 equals to a plus b, right? So the coefficients that have like x squared, x cubed, x, all of those, once we equate those things, we can just drop those. So here, really what we're looking at is that a plus b is equal to 3. when we equate the constants, it's already in that form. So we'll just rewrite this equation here. And this is the system that we solve to get what A and B are. We have two unknowns, we have two equations. So we can either substitute, we can eliminate, or if we put that in a matrix, you're eliminating. So you have two options, eliminate or substitution. So this, we'll still refer to this as equation 1, and we can refer to this still as equation 2. So we can either, for instance, we can take equation 1, solve for B, plug in equation 2. We can take equation 2, solve for A, plug that into equation 1. Or we could eliminate A by just subtracting these two equations from one another. So if I take equation 1 and I subtract off equation 2, what that gives me, I'll rewrite it here, 3 is A plus B. And then I'm subtracting off this equation, 5 equals to A minus 5B. So we have 3 minus 5, which gives us minus 2. A minus A is 0. We have B minus 5B, which is 6B. So that tells us that 6B is negative 2, which tells us that B is equal to negative 3.
What if you negative 1/3?
Oh yeah, negative 1/3, sorry. Yeah, B is negative 1/3. So then once we have B, we can find A. But if you had like 3 equations and 3 unknowns, you've got to add or subtract or whatever, eliminate another variable to figure out what B is. Then you plug A and B in to figure out what C is. So if B is negative 1/3, then we can let's just use equation 1. It says that 3 is equal to A plus B, which we now know is negative 1/3. And that allows us to solve for A. So we add 1/3 to 3, which gives us A is 10/3. Does that make sense? So I did mention when we first started looking at integrals, the process of integration is a very difficult thing. We see we have a whole lot of techniques just to figure out a seemingly, simple function, right? A rational function, they're pretty well behaved, but finding the antiderivative of them can be very difficult, as indicated in this process. That's the hard way applying to any one of these partial fraction decompositions.
That's the answer.
Well, so we've got to go back up to this thing right here and put in our 10/3 and our minus 1/3 there, because that's what our original function is equal to. So actually, before we do that, take this. Yeah, copy that. And we can look at the easy way. Just a reminder, this way does not always work. what we do is we have a factor of x plus 1 attached to a. If we let x equal -1, then that factor attached to a is gone, right? So let me see this. We have 3 times -1 plus 5 equals to a times -1 plus 1, which is 0, plus b times -1 minus 5. So we have -3 plus 5. We get 2. That's 0. And then we have -6b. We have -6b equals to 2. Which gives us b is -1/3.
We choose -1 because of the x plus 1.
Yep, exactly. And to get b, all we have to do is choose x equals to 5. And then, or sorry, to get a. But really, we've got just 2 things we're solving. Once I have b, I can find a. But in the manner that we've written this out, it's easier from this point to choose x equal to 5 to get rid of b. Is that right? Okay, yep. So we have 18 is equal to 6a plus 0. So, well, is that right? No, 15 plus 5. Sorry, y'all. All over the place today. Okay, so then we get the result that we came up with earlier in a much easier way. But you could imagine, for instance, like if we had repeated factors, we could have a times x plus 1, b times x plus 1 squared, c times x plus 1 cubed, right? And if we let x equal -1, like all of those would vanish. So it might be helpful, this way might be helpful to solve for one variable, but it wouldn't give us, you know, like what a, b, and c were, for instance. So it doesn't always work. Now we have to take our a and our b, go back up to this right here. So now we know the original function that was factored like this. Now we know what it decomposes into. A is 10/3 and b was -1/3. Oh wait, what happened? Where's the rest of this stuff? There was a problem right here. It just disappeared. Well, that's weird. I'll just rewrite it. What is x squared minus 4x minus 5 dx. Okay, then, so once we know how this integrand is decomposed, then we're going to rewrite that. That's equal to the integral of 10/3 over x minus 5 minus 1/3 over x plus 1.
That's pretty easy then at that point.
Yeah. So now we've took something that was hard to integrate and turned it into something that's easy to integrate. What would the antiderivative give us for this?
10 over 3 ln of x minus absolute value of x minus 5
Right.
minus 1/3 ln of x minus absolute.
Yeah. So now these are, both of these terms are in log form. We look at them like this. Derivative of the bottom is on top, so you got 10/3 ln absolute value of x minus 5 minus 1/3 ln absolute value of x plus 1. Of course, when we take the derivative, we're back here, which leads us back here. And to see that that's equivalent, then we would just need to add these two things together. When we add those two, we get 3x plus 5 over x squared minus 4x plus minus 5. Yep.
That's the easiest way, like, there's no other way to look at it.
Not for this one, yeah. We could, the only other thing we could do is complete the square on this, use substitution, split it into two different integrals, like that previous example from the last section. So yeah, that's pretty much the only things that we have.
The example where you were like, this is easier in the next section. That one?
Yeah, the last section, where it was a u squared plus 36.
Yeah, that one.
Yeah, that one. So we have that method too.
Seems like a lot less steps.
Yeah, so that works when you're dividing by a quadratic, right? You can complete the square on the quadratic, use substitution, split it up. But what if this is like a, what if it's like x minus 1 to the 4th power? Like, you're not going to be able to complete the square on something to the 3rd power, or the 4th, or the 5th, or the 6th, etc., right? So this completing the square, splitting up, does have limitations as well, and it won't cover all rational functions. This is actually similar to that one, so I think we're going to skip this. But I will write some of the components down. Now, just be mindful of how you set this up originally and what you're putting your A and your B and your C or whatever over, because you have to plug those back in exactly how you set that up. I know I can write this integrand as A over x minus 2 plus B over x plus 1, right? So that's one option. But somebody else could have factored this and they say, well, this factors as x plus 1 times x minus 2. Therefore, they would have, yeah. It doesn't matter, but the coefficient that above x plus 1, whatever you get for A here, you would get for B here. So however you set it up, just stick with it. Okay, so that's our setup, solve for A and B. A is 5, B is 3. And so you should come up with the answer. As ln absolute value, 3 ln absolute value x plus 1 plus 5 ln absolute value x minus 2. So simple linear factors on that one as well. Does everyone have what they need from this?
Yes.
All right, so here's an example when the shortcut doesn't work. So this time we do, it's already factored for us, which is nice, but it's a linear factor that's repeated. So how would our setup look like on this?
X plus 1, b over x plus 1 squared plus c over x plus 1 cubed.
Okay, good. A over x plus 1, b over x plus 1 squared, plus c over x plus 1 cubed. And what does that equal to?
X squared over x plus 1 cubed.
Almost, yeah, it's the original integrand, x squared over x plus 1 cubed. So here we're multiplying through by x plus 1 cubed to clear the fractions. So we have x squared equals to what?
A times x plus 1 cubed.
Okay, a times x plus 1 quantity squared
Oh, squared.
plus
B times x plus 1
b times x plus 1
plus c.
plus c. So the issue with the short way or the easy way, if we let x be negative 1, it's going to get rid of the a and the b. It will allow us to solve for c, but that doesn't help us in solving for a and b. Yeah?
Why wouldn't b be like b times x plus 1 cubed?
Well, because what we're doing at this point is we're multiplying both sides by the denominator here. And x plus 1 cubed over x plus 1 squared is just x plus 1. So that's why it's better not to think about just cross multiplying, because it's not quite that. In case where you have two simple linear, it's equivalent to that. But all right, so we're going to go through this the long way. We're going to say then x squared is equal to, we've got to expand x squared plus 1 and then multiply a through. So we have ax squared plus, let's say it's 2ax plus a plus bx plus b plus c. Y'all all right with that? Are there any questions? Keeping in mind that we have to equate the coefficients, we just have the x squared over here. So what we're thinking about is this is 1x squared plus 0x plus 0. And that means we have, let's do this here, our x squared equal to ax squared. And that's it, right? That's the only x squared term we have. So we have x squared equals to ax squared. Which means, what does that equation mean? Yeah, a equals 1. We have our 0x equating to 2ax plus bx. And that equation tells us that 2a plus b is equal to 0. Can we solve that? Yeah, because we already know A is 1. So we might as well solve that. So that's 0 equals to 2. A is 1 plus B. So that means B is equal to -2. So I'll circle these. B is -2. A is 1. And then finally we have our constant 0 equated to A plus B plus C. Again, we know A and B. So we know that 0 is 1 minus 2 plus C. So we have C plus, or C minus 1 is 0. That means C is equal to 1.
It's easy.
Any questions on that? Okay, so then we take A, B, and C, we go back up here and plug those in for our A, B, and C.
A lot of these are just going to be logs, right?
Yeah, a lot of them are logs, some of them aren't. It really just depends on the denominator. So the A was 1, we have 1 over x plus 1, plus B was -2, so we have -2 over x plus 1 squared, and C was 1 over x plus 1 cubed. Let's do that down here. Space. I'll just copy that and make it different. All right, first one, 1 over x plus 1, that's in log form. What about the -2 over x plus 1 squared and the 1 over x plus 3 cubed?
Minus 2L.
So we have to be careful with those, right? Because the derivative of the bottom function isn't the top, right? This is going to be a quadratic, so the derivative would be like, what is it, 2x plus 2, right? And the derivative here is even more complex because it's a cubic.
U substitution.
Yeah, so I think the easiest way to see those is with the u substitution. So for this one, let's let u equal to x plus 1.
One row.
Du is dx. And then for this one, we'll let v, let's say v, I guess, equal to, well, let's not use v so we don't mix that up with the integration by parts. Let's use s, yeah, w, whatever. S is x plus 1, ds is dx. We have that one. We have -2 times the integral. And then this is going to be 1 over u squared. So we'll call that u to the -2. This one's going to be s cubed, or sorry, 1 over s cubed, so it's s to the -3 dx. yes. All right. Like we said, the first one is in log form. The second one, we've got -2 antiderivative of u to the -2 is negative u to the -1. It's going to be a positive 2u to the -1. And then here, we've got a s to the -2. Sorry, yeah, s to the -2 over -2. And then we just resubstitute x plus 1 in for those. And maybe you don't need a u substitution there. Because again, the derivative here is linear. The derivative of the inside function is x plus, or the derivative of that rather is 1. Kind of like with that inverse tangent one. Do y'all have any questions on any of this? On a scale of 1 to 10, how difficult does this seem?
It seems difficult, just like
A 5 or a 9?
Divided his answer by 4.
All right.
I mean, we're just building on tools right now to kind of do more advanced stuff later.
Yeah, which we don't have time to do, but yeah. Okay, irreducible quadratic. So, for example, what would the partial fraction decomposition look like for 2x plus 1 over x squared plus 121? Say that again. Well, that mouse is spazzing out. That cursor was spazzing out. So that's our breakdown, right? So this is, we would say equate this to ax plus b over x squared plus 121. And like our previous example, this wouldn't really help us out, would it? Because it tells us that a is 2 and b is 1. Kind of stuck there, but that's the idea. How about for 18 over x plus 3 times x squared plus 9? So now we've got mixed, simple linear, irreducible quadratic.
A over x plus 3 and bx plus c over x squared plus 9.
A over x plus 3 for the simple linear, and then for the irreducible quadratic, we would call it bx plus c over x squared plus 9. How about number 6?
You got 2 linears.
Yeah, so x is linear, x plus 1 is linear. So that's, I won't be able to fit it all, but we'll start here. So we have a over x plus b over x plus 1. Then what? Well, would it be c over x squared plus 4?
With the cube, there's a cube.
Yeah, but what's in the cube?
So
it's a quadratic. So it's a repeated irreducible quadratic.
So AX. So CX plus D
Cx plus d over
X squared plus 4
x squared plus 4 to the first power. Yeah.
plus EX plus F.
Plus ex plus f
X squared plus 4 squared.
over x squared plus 4 to the second power. Gx plus h over x squared plus 4x to the third. Then what?
I over x plus 2.
Yep, I over x plus 2. Plus
J over x plus 2 squared.
j over x plus 2 to the second power.
We won't have to do this on a test.
Yeah, that's one of those will be on the test.
But just that part.
Just kidding. No, that would take way too long.
But I mean,
Yeah,
just
it
that
would.
part. We can just do that.
Yeah, you could just do that part.
We should do that.
Stack up, do not evaluate.
Yeah, do not evaluate. Just break it down like this. Just set it up. That could be a question.
That's how the trick stuff is, bro.
Okay, so here's a portion of that. We've got our we've got a simple linear and an irreducible quadratic.
Yeah.
Okay, so we've got the 18 over x plus 3 times x squared plus 9. Did the problem go away? Let me do that. Oh.
It's big now.
Yeah, it is.
If you break it, that happens.
The software is eating the problems. It's so weird. All right, well, get to work.
Quick before it vanishes.
I'm going to rewrite this.
I just multiply.
By the other. I got it.
So I just multiply both sides by this.
That just equals 18.
I like to write it as.
Are we writing this also as like 0x squared?
Yeah, you can do that if you need to. If you can keep track of the coefficients easily, then I wouldn't worry about it. we couldn't subtract one from the other because this one's AB, this one's BC, and this one's AC.
Oh, no, it's 3.
So we can substitute, right? We can't use elimination because yet we can't because there's not two of the same things in each equation. But that first equation tells us that A is negative B. So then we can turn equation 2 into an equation involving A and C. And then we have a third equation that involves A and C. We can solve for A, solve for C. Or we could do that with equation 2. We could plug in, or equation 3 rather. We could plug in negative B for 9 times A. Add that to the equation above.
Oh, that's a negative.
So another thing we could do if we're really trying to solve this equation here, right? Notice I can let x be negative 3, and it would eliminate all of this stuff, allowing me to solve for A. So if that system is like giving you issues, consider in the equation that we just started to let x equal to, what we say, negative 3. So we have 18 equals to a times x squared plus 9 plus our bx plus c times x minus 3, or x plus 3. And then all of this stuff right here would go away. 0. So we have 18 is 18a.
How did you know that x equals negative 3?
Because if I let x equal to negative 3 here in this equation, that whole thing is 0. It doesn't matter what this is, it's 0 times all of this, which is 0. So sometimes you can combine the long way and the short way. We're still going to have to default back to this system that we came up with, one way or the other. So A is 1. And we know from that first equation that A is negative B, right? So we can determine what B is. Now we have A and B, we can find C. Really, we just need A to find C, or B to find C from equation 3 or equation 2. So what is B? Okay. So let's say let's refer back to equation 1, where it says A is negative B. So B is negative 1. And then if B is negative 1, we can find C. Yeah. 3b plus c is equal to 0. So we'll plug this into equation 3. It says 0 is 3b plus c.
Equation 3.
Equation 2. Yeah, 3b plus c, equation 2. Thank you. So there's our A, B, and C. Do you have any questions? So we're right here. A was 1. B was -1. C was 3. All right, so are those easier or easy to integrate? First one is?
Just split up the second one.
Yeah. So that second integral, we're going to end up splitting that up into 2. So I'm going to make a note, split this up. So we've got log form for this one. When we have the split it up as -x over x squared plus 9, what does that do for us? Yeah, it's almost in log form. We just need the times the 2 divided by 2, right? And then 3 over x squared plus 9, what is that? Yeah, well, what? Did you say tangent?
1 over 1/3. Arctangent.
Yeah, the inverse tangent. I don't know. I heard someone say tangent.
That might have been me.
So that's after we split up. All right. Again, the middle one is almost in log form. Derivative of the bottom though is 2x. So we need the 2 here, which means we need the 1/2 here. So we've got the natural log absolute value of x plus 3 minus 1/2 ln x squared plus 9 plus, what do we get for that third one?
What is it? 1 over 3 arctan x
Over 3, yeah. So we've got a 1/3 arctangent of x over 3, which cancels with this 3 right here. So this is just inverse tangent of x over 3. All of our constants here.
Oh, the 3 cancels out.
Yeah. Are there any questions on that example? So finally, we want to consider when we have an improper fraction. Yeah, so we need to do long division first. And maybe we can talk about this on Tuesday. But long division turn this into the integral of 2x minus 1 plus 7x plus 1 remainder over divisor, which we factor as x minus 2 times x plus 3 for this thing right here. Okay. So after long division, we express that like this.
Well, we're not gonna go too far.
We can. I just want to put a nail in 8.5. And then here is your partial fraction on this one. So you might try over the weekend, if you have time, try that long division, see if you can get that result. If not, we can certainly talk about it. But then our answer is x squared minus x plus 3 ln absolute x minus 2 plus 4 ln absolute x plus 3 plus c. So if you want to try that one and you get stuck, let me know. We'll finish that on Tuesday. Otherwise, we're going to start 8.9 on Tuesday.